Okay, so here we have a lesson on distance, position, and displacement, and the difference between these three terms. It's really the start of our unit on kinematics. We've got some essential learnings up here that are important to go over before we start. So one of the reasons why this is important is because all matter is in a state of constant motion. So in the junior sciences, even in chemistry, we know that all matter is constantly vibrating. And when we get to things that have an appreciable size, we can actually study how they move, right? And that's what kinematics is. It's the study of how objects move, concrete objects. And we're going to see as we go through here, there's two types of motion. There's uniform motion and there's non-uniform motion. So a couple definitions to get us started. First up here is uniform motion, is motion in a straight line at a constant speed. Okay, and so this would be an example of this would be a car going in a straight line on cruise control on a road. Okay, so not up and down, not side to side, one direction and at a constant speed. Okay, non-uniform motion in contrast to that is motion where there is a change in speed or direction. Okay, and so when we did the inquiry activity with the cart, you would have seen, of course, that the physics cart had constant speed, right? So, and that was constant motion, straight line for the most part, and a constant speed. Whereas the pullback car had an increasing speed, which is different. So those are two very different types of motion. All right, so we want to take, before we get into what these, kind of what these three things, bang, 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 what these mean, we got to look first at a little bit of background. Okay, so let's talk about what vectors are and what scalars are. And this is a very, very light introduction. So a scalar measurement, these are two different types of measurements. A scalar measurement has a magnitude and a unit. Okay, and so typically these would include, say, a distance of 24 meters. Okay, so we have a magnitude, which is a size, and we have a unit. Milk, if you buy a 2-liter carton of milk, that's a scalar measurement. Also, we could say a speed. He was traveling at 6 meters per second. And last but not least, another example would be a mass, say 75 kilograms. Okay, so again, a magnitude and a unit. Where a vector is a little bit different, they have, of course, a magnitude. They have a unit. But vectors also have a direction. And this is an important distinction because it gives us an extra piece of information, and that's a good thing. Okay, so a magnitude, a direction, and a unit. And so an example of this would be 16 meters north. Okay, would be an example of this. Or we could say the car was traveling 75 kilometers per hour east. Okay, so these are examples of vectors. Now there's some things that, of course, really a vector wouldn't make sense. And so mass is something that isn't a vector. Mass is a scalar. And so we could say, all right, well, we're never going to say 75 kilograms left or 75 kilograms right. Like, it just doesn't make sense. Same with volume. Volume doesn't have a direction associated with it. But there are certain things like the separation of 2 points or how fast something is going that makes sense when you add this extra piece of information, and those are vectors. And really, we're going to talk a lot about vectors in this unit, and so it's important that we get comfortable with them as quickly as possible. All right, so moving on, we've got some notation. How do we um, differentiate between a vector, what's a vector and what's not a vector? And so we distinguish them by with special hats that we put over the symbols. And so a typical example would be speed and velocity. Okay, so let's talk about speed. Speed is a scalar. Okay, and we give it the symbol v, but the vector notation of speed is velocity. Okay, and we have a special symbol. Again, it's v, but we give it this special hat that's like a little arrow. Okay, so same thing, but we know that this then is a scalar. This right here is a vector because it has this little hat over top of it. Sometimes you'll notice that this can be shortened. Instead of doing a full arrow, sometimes we can do a little half arrow. This is also acceptable. It's just another form in physics. Sometimes in mathematics they'll ask for a full arrow hat, but most of the time in physics you'll see kind of like a half arrow. All right, and some sign conventions, because these are really, really important. Anytime when we, of course, are talking about north, south, east, and west, we're going to use some sign conventions. And so let's look at the compass first of all. The compass is an important tool for navigating. This is, of course, north, south, east, and west. And in the Cartesian coordinate system, okay, so just pretend that this is a grid and we've got an x and y axis. We know that up is positive and down is negative. And we know that in x and y, in this direction towards east, this would be positive x, and towards west would be negative x. And so this is a very typical sign convention that we're going to use. A little bit later on, we will see something very similar to this, but instead of, this would be like for a flat surface. Right? So if you're kind of driving around on a flat road, you could use north, south, east, and west. But when we flip our convention into kind of an upright direction, we could also have, and you will see this a little bit later on in the unit, we could also have left and right and up and down. And so again, same sign conventions, positive and negative, and positive and negative. Okay, so keep these in mind, because we're going to get into now a little bit more on using vectors and how we see them in day-to-day life. All right, so let's talk about these three things: distance, position, and displacement, because they all kind of refer to the obvious. They all refer to kind of where something is, you know, how far it's moved, but we need to be specific about our definitions here. Okay, so for example, distance, if we're going to do a definition, is the total length of the path traveled by an object in motion. Okay, and so that's what distance is all about. Total length of path that's traveled. And so we could talk about, I have this little section of map here. We're gonna draw a little coordinate system. Here's north, here's south. And so let's say that in our coordinate system, some person walks from here, the attendance office, and they walk down here to the meeting room, and then they decide to turn around and they come back and they go to the guidance office, what we would do is we would say, oh, well, how many meters does it take to go from here to here? Okay, and then they turn around and then they go from here to here. All of these things, we would add up all of these different distances, and that's basically what distance is. Okay, and you know that's a pretty standard definition of distance, and you know, that's something that for most grade 11 physics students, you know, you're pretty comfortable with. Position is a little bit different. Position is, if you want to define it, the distance and direction of an object from a reference point. Okay. Now, most of the time, if we're dealing with, say, like a Cartesian coordinate system where we have an origin, like a 0 point, then it's really easy to find the position of a dot or a, you know, an object, no problem, right? Because we have a very standard coordinate system that we can use. So, but not so when we're looking at things like this. So let's say, of course, this right here, this is 0. So here's 0. Then we could say, okay, well, let's say someone is standing on the stairs going into the balcony. Okay, that would give their position, because with reference to this point right here, we would know where the person is standing. Now, this is a vector, okay, because it's not just a scalar. Distance is a scalar. We don't care what direction the person's traveling. It's just the total length of path. But position is a vector, because if I said that the person is standing 16 meters from this point, right, where we go like this, and here's 16 meters. Well, we need to be specific about that, because 16 meters could also be over here, right? You would see that, oh, right, there would be 2 possible spots. So this would need to be 16 meters north of our reference point, okay? And that's kind of how we distinguish between a distance and a position. A position is the distance and the direction of an object from a reference point. So now we're going to put these things together, and we're going to talk about displacement, because displacement is something, again, similar but distinctly different. Displacement is the change in an object's position. Okay? And so if we want to talk about what these things are, distance is d. Position is a vector, and displacement is change in position. Okay? So this would be like saying, oh, it went from this position d2 to this position, or sorry, it went from this position d1 to this position d2. And remember that that's what delta means. It means 2 minus 1, right? So final minus initial. That's what the delta means. So this is kind of the 3 topics. What I want to do now is actually go right into how we're going to use these in an example. Okay, so here it is. So this is a floor plan diagram. This is actually the science hallway at KCI. Okay, and you can see that everything's kind of mapped out on here. Here, this is, of course, Ms. Getz's class. Here's Mr. Van Brunschot's class. Here's a chemistry lab. Here's this. Here's our room, room 220. This is our physics room. And so what we're going to do is we're going to kind of navigate through A, B, and C. Okay. So the first thing that we need to do is we kind of need to put some kind of a convention system in here. And so what we're going to do, I'm just going to do this. You know, really what we want is that we want to do ruler, nice straight line, and so we've got east and west. Okay, so just, we're going to say that this is east down here. This is plus. This is west. This is negative. All right. So we have a position, a coordinate system, which is good. We always need to start that. So you walk from the science office. Science office is here in room 222 to room 220. What's your displacement? Okay, so the first thing that we need to do is we need to make something 0. And so what we're going to do is we're going to make this position right here outside of the science office door. That's going to be 0. Okay, and so what we say then is we say, okay, in part A, we have a couple things that we need to know. First of all, our position 1 is at the science office. And relative to our coordinate system, our position initially is equal to 1. Sorry, is equal to 0, right? Because that's where we are. Our position relative to the axis is right here. Well, we're at 0. So that's our first position, okay? Our second position then is at room 220, because the question says, hey, you go from here to here, here's 220, and what we're going to say is that this is about 15 meters to the east, okay? So right here we've got our second, this is 15 meters, and we're to the east of our coordinate system. You see that? That here's 0, and here's our 15-meter mark, but it's in the east direction. So the question then says, hey, wait a second, what is the change? What's your displacement? So what's the change in this position? So we say, okay, delta D, which is our symbol for displacement, is equal to D2 minus D1, and we get 15 meters east minus 0. And so we can say, well, our displacement was 15 meters east. Okay? And that's kind of how we do these. So we're going to take another look at this now. We're going to take a quick look at part B. What is your displacement if you walk from room 231, okay, right here, to the guidance office? Okay, so what I want you to do is I want you to try this question. Kind of on your own. Given that, all right, well, let's do some estimation. So this door right here is at, we're going to say, approximately 11 meters, right? So from our coordinate system, this is about 11 meters. And the guidance office, well, this is kind of an extra 4 meters, so we're going to say that this right here is about 19. Okay, so given that, what's displacement 1, what's displacement 2, and then what's position 1, what's position 2, and then what's your displacement? So I want you to try that now. And what you should find if you've tried this question, don't peek. I want you to try it first and then come back to it. I'm just going to give you the answer. "8 meters east." That's the answer that you should get. Following this question as a template, try this. All right, and now we're going to do C, last but not least. So you walk from the science office to the guidance office and then to Van B's room. Okay, so you go from here. I'm going to put little orange highlighters on here. So you go from here to the guidance office and then all the way back to Van B's room, which is kind of -5, right? Because it's to the west 5, so we stick that minus in there, it's -5. All right, So this one is very interesting. This is a very kind of interesting question that we're going to go through, because this is a compound displacement. So this is what we know. Position 1, you walk from the science office, which is 0, to the guidance office. And position 2 is 19 meters east. And then you walk all the way back to Van B's office. So what we need to do now is we need to say, all right, we want to know an overall displacement. And what we could do is we could say, hey, let's do this in steps. Let's find out the displacement here to here, and then we'll find out the displacement from here to here. But it turns out that displacement is where did you start and where did you finish, and how far was that, right? So what we could do in this case is, instead of doing 2 steps, we could say, hey, how far did we go here to here? So we're going to do the displacement part first. And we're going to say minus 5 meters minus 0, because that's where we started. And so we get minus 5 meters is our displacement. And the negative right here indicates, oh, wait a second, we said that west was negative, so this means 5 meters west. Okay, and so that's how we do that. Finally, if we're going to be asked to kind of say, oh, what's our total displacement, because that's part, or sorry, what's our total distance that we've walked, then we can say, okay, now we take a running total. Okay, so when I went from 0 to 19, I walked a total of, so my distance is equal to 0 to 19, well, I walked 19 meters, plus, then I walked another 19 meters back to get to 0, and then I walked another 5 meters up to Van B's room. And so if you do this calculation, 38, 43. And so that's the total distance we walked, even though our displacement was only 5 meters west. And so you'll see that these two numbers don't agree, and they shouldn't. All right. Our last question is kind of a question for you to try on your own. I've left the answer right here for you to see, so you should copy that down. Dog is practicing for an agility competition, leaves his trainer, runs 80 meters due west to pick up a ball, carries the ball 27 meters due east and drops it in the bucket. What's the dog's displacement? So if it helps, you can draw a diagram, but this is the answer. This is the answer that we have right here. And so this is, of course, asking displacement. So why don't we be very specific about this? We'll put the dot, we'll put the triangle there. And so here's your answer. Try this question out. We'll take it up tomorrow.